Good morning, my name is Rafael Benach. I am a student of the Federal University of Paraíba, Brazil, and I'm going to present the work entitled An Optimization Method Based on LORA Parameters for Energy Consumption Reduction. This work has also as authors the Professor Cleonilson Protásio de Souza of the Federal University of Paraíba, Brazil, and the Professor Orlando Baiocchi from the University of Washington, Tacoma, USA. Here's the summary of my presentation where I'll talk about the energy consumption in IoT sensor nodes, some important remarks about LoRa networks and the LoRa parameters, and the proposed optimization method in this work explaining the optimization conditions and the calculations of the values of the transmission time calculations. Next, I'm going to explain the optimization algorithm we have developed. Finally, I'll expose some experimental results and the conclusion. As we know, the Internet of Things, that is, IoT, is a concept in which objects or things are interconnected by the Internet. A thing in the IoT context has incorporated some embedded electronic and data communication capacity that allows it to communicate with the Internet using technology such as Bluetooth, Wi-Fi, 4G, and LP1. In general, IoT things are powered by batteries or directly in power outlets. However, in some contexts, battery use is not suitable, for example, in natural environments, because these are potentially harmful. In these cases, an option for powering the sensor nodes makes use of energy harvesting. Energy harvesting is the use of techniques for collecting, power conditioning, and storage of available energy in the environment around the device that needs to be powered. For example, energy harvesting can use solar energy, thermal energy, electromagnetic energy, and others. In this figure, we see an IoT device that uses energy harvesting. We see here in head the energy transducer. Below, the power management circuit and a storage device, normally a supercapacitor. Next to there is the common part of IoT devices, a microcontroller, sensors and the radio to allow wireless communication. Another important issue is about the wireless communication technology used by the radio. As we know, the radio is the piece of hardware that consumes more in a sensor node. A solution is to use low power, wide area networking technologies, that is LP1, since it is shown to be the best solution since they are oriented for low power. Nevertheless, despite the low power capabilities of LP1 technologies, the LP1 based IoT devices still need further research for decreasing even more the energy consumption. In general, the data transmission system is the highest responsible for energy consumption, as can be seen in this figure that shows a power consumption pattern of IoT sensor nodes. In this way, the greater the power reduction of the transmission stage, the more the sensor node saves energy. In general, to achieve low power and low range, LP1s use robust modulation techniques. For example, LoRa is based on the sharp spread spectrum, that is CSS modulation. In short, a chirp is a signal that has its frequency varied linearly, crescent or decrescently, and the variation of the chirp frequency is used to encode data. In this figure, we see the general LoRaWAN network architecture, where the sensors connect to the gateways using LoRa communication and after that the data go to servers using the internet. It is important to note that LoRa is the physical layer of the LoRaWAN protocol which uses a star topology to connect the devices to an internet-connected gateway. Taking in consideration on the path between the sensor devices and the gateways where LoRa modulation takes place, it can be arbitrarily configured so that the data rate, the achieved range, and the transmission time can be modified by the main LoRa parameters that are the spreading factor, the bandwidth, and the coding rate. In short, the spreading factor, that is the SF, is typically an integer between 7 and 12 and corresponds to the number of encoded bits per LoRa symbol, that is 2 parts to SF. For this reason, and to maintain the high sensibility, the higher the SF value, the longer is the time on air, that is the TOA. The bandwidth, or BW, is the difference between the higher and the lowest frequencies a chirp can assume along its modulation. The possible values of BW vary according to local rules, although common values are 125 kHz, 250 kHz, and 500 kHz. The increase in bandwidth implies increasing the data rate and reduces the transmission time, reducing the communication range as well. The coding rate value refers to the amount of data bits used in relation to the total number of encoded bits. Another parameter that can influence the consumption of wireless network is the package size to be transmitted. Clearly, it is possible to notice that the TOA is proportional to the package size. Thus, changing the package size, the energy necessary to transmit data is changed as well. In addition, it is possible to adjust the transceiver's transmission power following the range of possible values. Commercial LORA transceiver power range is generated from 0 dBm up to 23 dBm, although this range depends on the specific radio model. Some general information about RF packet transmission are the transmission power, sensibility, RSSI, path loss, and link budget. So regarding the antenna gains and the cable losses, the image shows the relation between those. The transmission power is the power with which the package leaves the transceiver radio. The sensibility is the lowest power with which the receiver is able to receive a message. The link budget is the difference between the transmission power and the receiver sensibility. The RSSI, that is, the received signal strength indicator, is a power indicator in which a package is received by the reception radio. The path loss, or PL, is the loss of signal power associated with the package trajectory. Then it can be calculated as the difference between the transmission power and the RSSI of a message. Therefore, for a message to be received, the link budget must be greater than the path loss. The transmission energy can be calculated based on the transmission power, that is PTX, multiplied by the transmission time, that is TTX, and it is a function of the spreading factor, bandwidth, and some other parameters, such as the packet size. In order to optimize the transmission energy PTX times TTX, we have to find combinations in which the path loss is less than the link budget, that is, the difference between the transmission power and the sensibility. The sensibility is also a function of the spreading factor and bandwidth. The spreading factor and bandwidth variables are discrete, then it is possible to solve this problem iteratively. Some values of SF are 6, 7, 8 up to 12, and some examples of bandwidth are 125 kHz, 250 kHz, and 500 kHz. In order to solve the optimization problem, a computer program was made following this algorithm over here. First, we create a collection with common path loss values. Then we iterate through this collection and find the combinations that satisfy the statement of the optimization problem. After this, for each combination that satisfies the statement in the path loss of actual iteration, the transmission energy is calculated and the combination associated with the lowest energy is the optimal one. As the main result of that algorithm execution, we were able to find the optimal configuration of the spreading factor, bandwidth, and transmission power to each integer PL between 30 dBm and 151 dBm for a LoRa payload with 3 bytes or more. In all the optimal combinations, the bandwidth remained with the value of 500 kHz. Then the bandwidth optimal values are not split in the graph. Each point expresses a PL value, and the other pair of its localization expresses its optimal configuration of spreading factor and transmission power, respectively. Also, for path losses inferior to 115 dBm, the optimal SF and PTX remain the same, that is 7 and 0 respectively. The dashed red rectangle indicates configurations of SF and PTX that did not result in minimal energy consumption for NPL. The optimal LoRa configuration set versus the PL values are stored in a two-dimensional array, a matrix that is easily stored in the sensor node memory, so it's not necessary to redo the computation, which would consume more energy and time from the sensor node. In order to compare the transmission energy according to the obtained configuration set matrix, a development board called Feather MO from Adafruit company was used. This board has an RFM95 LoRa radio module and a ARM Cortex-M0 microprocessor. To measure the power and the energy consumption of the Feather RFM95 board, the electrical current of the board's power supply was measured with an INA 219 based current module using the shunt resistor technique. The measured current data was collected by another Feather board that was responsible for getting the measured data and for serial communicating to a computer, where they would be stored for further processing and visualization. This measuring equipment was used in conjunction with the development board in order to create a system that could also make measurements in the field, so an oscilloscope with a precision probe was not needed. The value of the shunt resistance used for measuring current was 0.1 ohm, which implies a resolution of 0.8 milliamps. Also, the sampling frequency was approximately 665 Hz due to limitations of the communication interfaces. With the proposed system, measurements of 99 packets were carried out by the sensor node with the optimal setting for each PL value between 30 and 151 dBm, totaling 36 different configurations of spreading factor, bandwidth, and transmission power. Thus, using these measurements, the averages of consumption and transmission times were calculated. To estimate how variable the measurements of transmission times were, the standard deviation for each SF was calculated, as can be seen in the table of Figure 6. In addition, the distribution of the measured transmission times can be seen in the graph of Figure 6. The Figure 7 shows the visualization of the current pulses that flow through the feather when some transmission is done, and the variations in the amplitude and length of the pulses as a function of transmission power and spreading factor. In these graphs, we can see current pulses samples for some of the spreading factor and transmission power configurations. The bandwidth was fixed at 500 kHz. Also, this graph shows the difference in terms of energy consumption to send a message for each path loss with its respective optimal configuration. We can see that there is a big drop in energy consumption when there is a reduction in the spreading factor. We conclude saying that in the context of IoT, reducing energy consumption is very important to the sensor node's lifetime. And in some cases, such as those that use energy harvesting as an energy source, this power reduction is essential. Therefore, using low power network is a good option to reduce energy consumption, but it is also necessary to use the network and its protocols in an optimized way, adapting it to the use case. In the LoRa modulation protocol, it is possible to establish different configurations which fit the needs of the system, reducing the sensor node consumption. In this work, a method was developed to calculate the optimal settings of spreading factor, transmission power, and bandwidth. This method can be used to reduce the energy consumption in sensor nodes, estimating the best setup for of these parameters for a sensor node. Experimental results showed that the spreading factor had an enormous significance in the energy consumed by the sensor node to send packets. However, the range of the transceiver also decreases with the reduction of the spreading factor. Thus, The transmission time and RSSI can be essential information in the calibration of LoRa parameter settings. Otherwise, there is possibly a trade-off between the spreading factor and the proportion of received packages, which can be studied in future works. These are the references used in this work, and thank you all for your attention.